So here is a stage game, all right? And I'm going to look at, so this is, let's call it G, and I'm going to look at the game where this stage game is repeated infinite horizon, okay? And each player discounts future with a common discount factor delta. I don't know what it is at this point. Let's say it's greater than 0, but less than 1. Well, if you look at this game, and if I did it wrong, there is no pure strategy Nash equilibrium of this game, right? I mean, there's none. Player 1 plays A, the best response for player 2 is playing C. Player 1 plays B, best response is A, and player 1 playing C, the best response is C again. But if player 2 plays C, the best response is B for player 1, so there's no Nash equilibrium where player 2 plays C. If player 2 plays B, the best response is B, and if player 2 plays A, the best response is A. So as you see, we don't have any pure strategy Nash equilibrium, but thanks to Nash theorem, this is a finite game, so there must exist at least one Nash equilibrium. It's in mixed strategies, but forget about it. So now what I'm going to argue is that we can sustain non-Nash payoff throughout this game, whether they are rewarding each other or punishing each other. And this is what I'm going to show, and also what I'm going to show you is how strong the one deviation property is and how useful it is. I know a lot of students sort of skip that video or just say, well, okay, we got it. But, well, I mean, it actually is very, very important, not just for repeated games, but for analyzing any sort of extensive form games, especially if the extensive form game is one that is complicated, like, you know, if it doesn't have a simple game tree. If it has a simple game tree, well, don't worry about the one deviation property, but if you can't draw it, well, you will need one deviation property, okay? So here I'm going to talk about the following strategy, profile, okay? So play CC in period 1, all right? Then play AA forever. If player 1 deviates, I'm going to leave this strategy incomplete because I am going to talk about only player 2's perspective and just want to make a point. All right, so for that reason, I'm going to leave it unspecified. Some parts of it will be unspecified, so don't worry about it. So if player 1 deviates at any point, play CC right after deviation. Right after deviation. Because remember, although they play simultaneously at each stage, before they choose their actions in this next stage, they actually observe what their opponents did. Right? That's the idea of repeated game. We simultaneously choose actions, A, B, C, A, B, C. So when I choose my A or B or C, I don't know your choice. All right? But once the stage is over, I learn your choice, and then we move to the next period. So the next period, I know whether you cheated or deviated or not. And you also know whether I deviated or not. So right after deviation, and play AA afterwards. So basically, the strategy says, well, I mean, play CC, okay? And once this is some sort of punishment, okay? We're punishing player 1 because CC, I mean, it's clearly not Nash, and it's -5, right? If player 1 knows that his opponent is going to play C, he clearly wants to play B instead, right? But the thing is, if he plays C today, all right, and his opponent also plays C, they're going to play AA for the rest of the game. So it's like there's a reward. So don't forget, the repeated games are all about carrot and stick, all right? Or rewards and punishments. So you reward players by cooperating, on high payoffs. But if they deviate, because, well, I mean, everybody has incentive to deviate. Otherwise, I mean, that sort of high payoff vector would be Nash equilibrium. So if they deviate, you should punish them, all right? So how severe is this punishment, or does this punishment should be? Well, it depends on the discount factor and then how large the incentive to deviate, etc., etc. Okay? But that's the idea of infinite horizon repeated games. We can sort of use the future of the game as a carrot and also as a stick. So that is going to balance the player's incentive to deviate or not. All right? Which, by the way, we do this in real life, right? I mean, at least this is how a lot of parents sort of, force their kids to behave. And so as teachers, maybe everybody, I don't know. So that's it. If I play C today and suffer this -5, I know that future is going to be beautiful because it's going to be 2020. All right? But the thing is, if I deviate today, I'm going to get 15. And so tomorrow I will have to be, we are forced to play CC again. All right? So what I'm going to do, I'm going to show that this strategy profile, at least, part of this strategy profile, is actually a Nash equilibrium. I mean, it's a subgame perfect Nash equilibrium. It is a part of subgame perfect Nash equilibrium strategy. How am I going to show that? Well, simple. What is the player's one payoff if there's no deviation from this strategy in period 1? And then his payoff if he deviates in period 1, okay? So this is what one deviation property tells me. You don't have to worry about deviation for the entire game. Just focus on one period, one deviation, right? So in period 1, there's no deviation. So what does that mean? That means I'm going to suffer -5 today. So we're going to playing CC. But tomorrow and afterwards, we're going to be playing AA. And so I'm going to get 20 delta plus 20 delta square. Remember, I discount. So that's going to be my payoff throughout this entire game. If I stick to my strategy, well, remember, when we check Nash equilibrium, we always assume that the other guy will stick to his strategy, all right? So only one player is allowed to deviate in our analysis. So both players deviating at the same time, this consideration is out of question when we check Nash equilibrium, all right? Or subgame perfect Nash equilibrium. Player 1, but as you see, I am very excited about my lectures on cooperative game theory. There, we will actually care about what if more than one player wants to deviate, all right? Again, it's another story. So what if the player 1's payoff is if he deviates only in period 1 and then stick to his strategy for the rest of the game? Because this is what one deviation property says. Don't worry about deviating for the entire game. Just look at deviation per period. So in period 1, he deviates, and obviously if he deviates, he doesn't want to play A, right? I mean, it's 0. Yes, better than -5, but given that B is there, well, obviously he's going to deviate to B and get 15. Well, what's going to happen? Again, he sticks to his strategy, and as well his opponent. Well, the next period, they're going to play CC. So he's going to suffer -5, but he's just postponing it. And then afterwards, they're going to play AA, and so he's going to get 20 delta square, 20 delta cube, etc. So the thing is, this strategy is a Nash equilibrium if and only if U1 no deviation is greater than or equal to U1 deviation. Okay, so no deviation is this payoff, -5 plus 20G. Do I need to write this part? No, because they're going to cancel out. Because I have this term on both sides of the inequality, so I can ignore that. So I'll just write this, -5 plus 20 delta, greater than or equal to this, 15 minus 5 delta. If I solve this, 25 delta is greater than or equal to 20. Delta is greater than or equal to 20 divided by 25. If you divide it by 5, you're going to find delta greater than or equal to 4 divided by 5. It's like 0.8. So if player 1 is patient enough, meaning if his delta is greater than 0.8 or equal to, well then no deviation is a best response to player 2's strategy. Okay? Well, now let's criticize this one deviation property, because I think this is a very nice example. Here, one deviation property says all you have to worry about one deviation at a time, and then for the rest of the game he's going to stick to his strategy. But look, I deviated today and received 15 payoff. And tomorrow I play C and receive -5. Am I stupid? Of course I will deviate tomorrow as well. So I'm going to get another 15. And then, well, I can keep deviating actually. But let's say I don't want to deviate for the rest of the game. All right, so I'm going to say, all right, I deviated once and twice, and then for the rest of the game, I'm going to stick to my strategy. Let's check if this is going to change really anything. Well, so I calculate this payoff, U1, 2 deviation. Okay? What would be his payoff? Well, he's receiving 15 in period 1 because he deviated. In period 2, he's going to receive another 15. And then for the rest of the game, he's going to stick to his strategy. Remember? So it's going to be -5 delta square plus 20 delta cube, etc. All right, so now let's check if U1 no deviation greater than or equal to U1 2 deviation. So no deviation is again this one, -5 plus 20 delta plus 20 delta square. Why? Well, because remember, this time we don't have 20 delta square plus some other sum. We have 20 delta cube sum. So that term is going to cancel that term. So this 20 delta square will remain. It's not vanishing. So I keep it here. Greater than or equal to 15 plus 15 delta minus 5 delta square. The rest is going to be, as I said, sort of cancel out. So is this really the case? Well, let's simplify this. What do I have? If I take this, I have 25 delta square plus 5 delta. Is this really greater than 20? Well, remember, delta was some number greater than or equal to 4 over 5. Well, what if delta is equal to 4 over 5? Well, if delta is equal to 4 over 5, this is 25 times 16 divided by 25. 5 times 4 divided by 5. Is this really greater than or equal to 20? Well, this is 16. This is plus 4, 20. Exactly equal to 20. So it satisfies this inequality. Interesting. So even though I deviated today and tomorrow, I'm not going to be able to make or achieve higher payoff. Well, okay, but what about 3 deviations? Like I deviate today, tomorrow, and then one more period, and then I promise I'm going to stick to my strategy. Well, I leave it as an exercise. Do it. But you'll see that whether this guy deviates 2 periods, 4 periods, 5 periods, 10 periods, and then sticks to his strategy, it doesn't matter. Okay? Meaning, no deviation payoff is going to be greater than or equal to his deviation payoff as long as delta is higher than this threshold number. Obviously, you can ask, what if this guy wants to deviate forever? All right? Well, that's a good question I am posing to myself. But I'm also asking to you guys, what do you say? What if this guy wants to deviate forever?
Would that give incentive for the player 2 to deviate then? If he deviates forever?
I mean, let's suppose player 2 sticks to his strategy, okay? We are checking if player 1 has profitable deviation, all right? So that's the thing. What we just shown was that deviating 1 period or 2 or 3 And I'm promising you that deviating t periods is not going to help this guy. But what about deviating forever? Do you think it is going to help him? I don't know, to be honest. I mean, it shouldn't, because otherwise that would mean one deviation property is wrong. It's not, I know. So let's check if this guy really wants to deviate forever. 15 delta, 15 delta square, forever. So what do I have? Well, this time the calculations are not easier, by the way. So what do I have? U1 no deviation should be greater than or equal to U1 infinite deviation. Okay, so on the one hand, I have minus 5 plus, so this term, 20g parentheses 1 plus delta square forever, right? On the right-hand side, I have 15 parentheses 1 plus delta square plus forever. Okay, so what is this? This is infinite sum. But because delta is less than 1, this is a geometric sum. So this is 1 divided by 1 minus delta. Same here. Good. So what do I have? I have 20 delta divided by 1 minus delta minus 5 greater than or equal to, I'm sorry, I don't know why I put equal there. 15 divided by 1 minus delta. Multiply both sides by 1 minus delta. It's not going to change the sign of the inequality. I have 20 delta minus 5. 1 minus delta greater than or equal to 15, right? 1 minus deltas on the denominator will cancel out. So what do I have? I have minus 5 here. I send it to the other side, 20. I have plus delta. I mean plus 5 delta plus 20, so 25 delta. So delta greater than or equal to 20 over 25, which is equal to 4 over 5. Well, this my magical discount factor. You see what I mean? So this is the beauty of one deviation property. It just makes our life easier. We didn't really have to check all these, like 2 deviation, 3 deviation, infinite deviation. Because just stick to your damn strategy as long as your delta is high enough. Trust me, that gives you the best payoff you can achieve given your opponent's strategy. So that's what one deviation property says. And so you don't really have to worry about all this. All you have to do is just what I did. You know, one simple calculation I did and found 4 over 5. That would be enough to show that that strategy is in fact best response for player 1 against player 2's strategy. But obviously here we should also check, what about player 2, right? I mean, is he going to be okay sort of punishing player 1? Because he's getting 10. Actually, if player 1 is playing C, he would prefer to play 10. Yeah, well, you know what? Player 2 is going to be very happy of playing, C, given that his opponent is, keep playing C. But if he deviates to B, obviously he doesn't want to play C. But again, it's like when we do the same analysis, it's like, is this a best response for player 2 against player 1's strategy? We have to use, once again, the one deviation property, meaning player 2's payoff if he does not deviate versus his payoff if he deviates only on that period, all right, and only once. And then we need to find the delta, the discount factor.